Hello everyone, welcome back to another video for the series. I'm Inoku and today I brought a classic polynomial problem, and it's something related to irreducibility. So I'm going to solve this in two different ways. First one is the basic method, and the other one is something related to like number theory. And I think I mentioned this in my previous video, but I'll be making my videos primarily on algebra and geometry because I feel like I quite need to give up on combinatorics and number theory because I don't have enough time until the KMO Stage II, which is on November. And in terms of algebra, I was only studying inequality, and I was also making videos only about inequalities, functional equations, and summations. I had not really tackled polynomials because I just hoped in my heart that please no polynomial problems because polynomials are somewhat related to like abstract algebra and also algebraic number theory. So it was just something that's really hurt for me in algebra. So I was like, please, I don't want polynomials in my exam. But I realized that I also need to study more on polynomials because I only focus on the three, like inequalities, summations, and functional equations. So yes, so I think I'll be making more videos about polynomials and also more geometry problems. So the first way is like the algebraic way. I'm going to, oh wait, but before doing that, I'll explain what the meaning of the term irreducible and also this notation right here. So a polynomial is irreducible. I think I spelled it wrong. What? Irreducible. If a polynomial is irreducible in, I would say, over the integers. A polynomial is irreducible in integers if it cannot be represented as a multiple of integer polynomials, non-constant integer polynomials, sorry. Non-constant, because that's quite important, integer polynomials. And you can change this integer to like real, rational, or like even complex. So if you're going to change this word, you can also change this word. So a polynomial is irreducible in something if it cannot be represented as a multiple of non-constant something polynomials. So for example, x squared plus 2x plus 1, it is reducible in integers because we can represent it like this. And this is, so x plus 1 is non-constant integer polynomial. However, we can write this as a multiple of non-constant integer polynomials, so we can reduce this one. So reduce in integers, of course. I think one other example, oh yeah, this one is a good one. So 2x plus 1, it is irreducible because we cannot represent this in a multiple of non-constant integer polynomials. So every linear polynomial are irreducible. And I think another good one is like x squared plus 1. We obviously cannot reduce this because we cannot represent it. Yeah, we cannot. No, we just know that we cannot reduce this anymore because we don't have real roots. So if we don't have like rational root for a polynomial, then we could just say that it is irreducible in integers. Now I'm going to, so let's say k. This is a set of polynomials. Is a set of polynomials composed of monomials with coefficients in the set K. So is a set of polynomials composed of monomials with coefficients in the set K. Yeah, so I think this is a great definition. Yeah. So this represents the set of polynomials over the set of polynomials in real number. So sorry, the examples would be like what are some real numbers, like square root of 2x squared plus 2 over 5x plus like 19. This is an example. Also we could do like pi is a real number. These are all good examples, I think. And quotients. This one. Oh, it's not quotient, sorry. The rational numbers. In rational numbers. So, for example, it would be like x cubed plus 2x like minus 3, something like this. And obviously this one would be in integers. So for example, like 2x squared plus 5x and so on. And we also do talk about complex numbers here, but I mean we also have like complex numbers, but I don't know how to write this well, but we don't really talk about complex numbers. I mean we do, but like at least we don't talk about it when we talk about basic stuffs. So like complex. So for example, I think it could be something like this. Yeah. I think that's all we need for this. So let's prove this. Proof 1. So we need to prove that. Wait, actually, let me just copy and paste that problem. Oh. Why are they? It's quite strange. Why are they linked? I don't really like it, but oh yes. Well, so we're going to prove that this is irreducible. So proof 1. We're going to do a very basic approach. So first of all, wait, there's also one thing. There's a thing called rational root theorem, but yes, I will just quickly explain it while solving this problem. So rational root theorem states that if P over Q is a solution to where P where P and Q. So in here, okay, I will just if oh no, okay, if is a root of polynomial, then I believe so P divide is of 0 and Q divides A sub n. So this is rational root theorem. Then applying this here, we know that Q must be, because A sub n is here, equals 1, so Q is equal to plus or minus 1, and P is equal to P is equal to plus or minus 1 because A sub 0 is equal to 1 here. Therefore, the roots must be either rational root equals plus or minus 1, minus 1 if it exists. But let's substitute it. Of course, we know that we don't have a real solution because we don't have to use rational root theorem. I just used it because I think it looks cool to just like use theorems. Yes, actually we don't really have to use this. We know that because this is always greater than 0, has no solution over yeah. So that means, so this thing is saying the same thing as cannot be x to the power 4 plus 1 cannot be written as a multiple of written as a multiple of linear and I'll say cubic polynomial. So that means we know that x to the power 4 is equal to ax squared plus bx plus c times abcd dx squared plus abcd e f yes, where AD equals 1 and CF is also equal to 1. Is it right? Yes. Because we know that they're equal to 1 and AB so A equals D equals plus or minus 1 and C equals F equals plus or minus 1. Therefore, rewriting this, we have x to the power 4 plus 1 equals, let's just without loss of generality, oh no, actually yeah, this sums up everything, I think, because it includes every case. Because just multiplying -1 on both sides, then we know that we obtained I mean we used every case because B and E could also be negative numbers. So we actually did count every case. Yeah, just yeah, we did count every case. Yeah, because just multiply negative on here and here. Therefore, this is equal to x to the power of 4 plus, what's x cubed? We have e plus b. I'll just write b plus e. X squared plus 1. Is it 1? No, sorry. Plus or minus 2. X squared. How about x? Plus or minus b plus e x plus or minus plus 1. So therefore, b equals negative e. But if b equals negative e, we know that. However, plus or minus 2 is impossible, unobtainable, since, b yeah, I think this is right, because they must be a rational number. Yeah, because we're proving that it is irreducible in the set of polynomials over the rational numbers. Therefore, is because the contradiction occurred. Because for the sake of contradiction, we just say that we are able to factor it like this, assuming that a, b, c, d, e, f are all rational numbers. But then contradiction occurs, so we know that our first statement right here is false. Is irreducible. Yes, I kind of love this proof. It's quite basic. We don't need to use like advanced stuff. We just need like basic knowledge on it. Let's look at the second proof. And before we move on to our second proof, I quite want to introduce Eisenstein's criterion. And the reason why, I think in the beginning of this video, I mentioned that polynomials is quite related to number theory too. So when we usually say polynomials, it is under the category of algebra, but it's also like really intertwined with number theory. And Eisenstein, wait, I forgot to spell his name. Eisenstein? Is this right? Eisenstein criterion. Let so I'm going to explain what this is quickly. So let integers be defined as nxn plus like a n minus 1 x n minus 1 plus plus a sub 1 x plus a sub 0 is irreducible and if there exists if there exists a prime such that P divides a sub 0. Oh, what am I saying? Wait, is it right? P divides... Oh. P does not divide a sub n. P divides a sub I for all sorry, does not divide a sub 0. I think this should be right. Yes. So this is Eisenstein's criterion, and actually we know that this problem could be solved really easily if we just use Eisenstein's criterion, unlike our first proof. So let's use it. Let p of x equals x sub power 4 plus 1. And here's a slight trick here. If so, yeah, I'll just write it and then explain it. In irreducible in... Yes. And the reason is because if this thing is irreducible in here, this must also be irreducible in here. And the reason is because these are actually like, consider this function like f of x plus 1 and f of x. They're technically the same function f. So if one is irreducible, the other must also be irreducible. Because just think of it like this. Just you're going to substitute. So yeah, you're just going to substitute a bigger value. So I mean, sorry, smaller value. So you're going to shift it. So let's just think of it like this. You're going to graph it, p of x, and if p of x is irreducible in here, that means you don't have like, so we don't know what that is, like what p of x is, but we know that all the roots, these are not rational. Because if we have a rational root, we definitely could reduce p of x in a subset of polynomial, in a set of polynomials over the rational numbers. So let's just shift it, like shift by 1 unit. So we're going to, so this is p of x, and this is p of x plus 1. We obviously know that these are not rational either, if they're not rational, if these roots are not rational. So it's quite obvious to think of this one. Then we're going to prove the reducibility in here, so that this is irreducible in here. P of x is irreducible in here. In other words, it suffices to prove that p of x plus 1 is irreducible in set of polynomials over rational numbers. So p of x plus 1 is equal to x plus 1 to the power of 4 plus 1, and this is equal to x to the power of 4 plus let's use binomial theorem. plus 4 2 sorry, and it's 4 4 4 4 it's 1, so plus 2. Consider a prime number 2. P divides, so this is 4, this is 6, this is 4, so P divides a sub I for all. This is true. And P does not divide a sub n because a sub n is equal to 1. And also P squared, which is 4, does not divide a sub 0. Therefore, by Eisenstein's criterion, x to the power 4 plus 1 is irreducible. Reducible in the rational numbers. Yeah, so that completes our proof. Oh, I forgot to put a QED box here. Yes, so this was a very classic problem in algebra involving polynomials. I hope everyone enjoyed it, and in my future videos I'm going to include more videos on, I think, polynomials, because I actually do need to study them, like especially, but thankfully, like unlike inequalities, I don't think there are much more things to study in polynomials. So like it feels like for summations we need to study techniques, like, so whenever we see some like series, we should be able to see how we could somehow telescope it, and I think that's like the main kick for summations. And for functional equations, I think we just need to be smart in substitutions so that we can find f of x or like any other functions. But the thing is, we should really be careful that we satisfy the if and only if condition. So we found every functions. And for inequalities, we just need to like practice a lot, know lots of inequalities. But for polynomials, thankfully, I think we don't really have lots of problems from polynomials in like Olympiads, I think. And they're usually like in algebra, they're more intertwined with functional equations. But if you have like polynomials, then I think they're usually number theory problems. So that's really good for me, I think. And but sometimes like there are polynomial problems, and I think we just need to study like these kind of stuffs so to solve them. But I think we still need to study some more advanced stuff like Lagrange multipliers or interpolation, or like LTE, which is there's lifting, so I forgot the full name of it was, I don't know that quite well, so maybe I will study about that and make a video in the future. So this was my first video about polynomials. Thank you so much for watching this video, and I'll come back tomorrow with another very fun and interesting poem. Thank you, and see you tomorrow. Bye.